Is everyone ready? Okay, let's begin stage 3 of Physics Fight 4. In this stage, Australia will report, Germany will oppose, and Greece will review. So let's begin the stage 3 by challenging the problem from Team Germany, please.
Present problem number 1, the paper boomerang.
We reject the challenge.
Then we challenge you to present the second problem, the air muscle.
Yeah, we reject the challenge.
We reject.
Problem number 1 rejected. Problem number 2 was rejected. And then we have only
When there are
4 problems left. So those, should add more.
If you look here, please, on the green ones. So one is
You reject out of present whatever it is offered.
And if you have
You don't
nothing,
care. No, you present it. There was a case someone presented without provocation.
it seems that
I heard about the cases when people
Right.
just write
five,
synonym.
if the sedation
Rights generally
challenge something that they
other than that, like, what do you want me to offer? Because he's terrible for opponent as well.
What are you gonna say?
It's
This is even the competition anymore, like with applications.
so then we can also to
For their part, like
my understanding as well.
yeah, that's right.
Can you confirm? Okay.
for your part, that's
there are teams.
Sorry for this quick clarification, but then we are going to challenge you to present problem number 9, the magnetic assist.
Accept.
Okay, perfect.
The problem.
Because we need more, at least 5 problems to choose, and has been released. What's the order when? Nine is accepted.
So from this, what we first get is that we've got magnetic forces and magnetic fields, which are going to change the behavior of like a normal pendulum, because we've got this suspended from a string. And we're only considering attractive orientations of the magnets based off the attract. And motion, so how the position changes over time, and moving magnets, so the suspended magnet as a pendulum. So yeah, just an outline of terms used so we're on the same page. We've got suspended magnet. This is the moving pendulum. I'm going to talk about attractors, which are positions that the suspended magnet will tend towards. And magnetic-based attractors, I will call attractors that the restoring force near the attractor is primarily magnetic, and gravitational, where the restoring force is primarily gravitational. So I'm going to break this report down into the one magnet case, extend that to the two magnet case, and then our conclusion from here on out. So yeah, demonstration, explanation, model, and experiments is how we're going to do each things. So when we look at this, what we see is when it's far from the magnet, we get periodic predictable behavior like a normal pendulum. But when it's near the magnet, we get jerky motion, and that transition between it is unpredictable. This is chaotic, one of the simplest systems of chaos. However, the interaction between the magnetic, there's a magnetic attractor and a gravitational attractor. This hasn't been explored well enough, we think, in literature, so that's what we're going to focus on. However, we'll look at the two magnet case as well. So the magnetic force, it acts to align the opposite poles and bring them closer together, and it drops off really quickly with distance. While the force of gravity is trying to bring it closer, like to directly underneath the pendulum attachment, and it grows with distance from the center, so distance from the attractor. So why does the magnetic B field drop off so quickly? That 1 over r to the power of 3 isn't the normal 1 over r squared we expect with which is because we've got dipoles instead of monopoles. So the field comes from the fact that, yes, this is the limit, but the north pole will be slightly closer than the south pole, right? So you're looking in the distance, so the field there, you're looking at the distance in a 1 over r squared relationship. That ends up to be a 1 over r3 because the distance becomes proportionally smaller as you move further away as well. For that same reason, then the force between magnetic dipoles is proportional to 1 over r to the power of 4, right? You've got a force on the south pole in this case, which would attract it to the first magnet, and you've got a repelling force from the north pole. But since the south pole is slightly closer, it's got a larger force. Yeah. So what are the forces involved here? We've got tension pulling it up. That means that we're not going to have the magnets snap together, because the magnet is also attached on the base, according to the problem. We've got the force of gravity pulling down, and we've got the magnetic force pulling it towards the magnet. The simplest case is when there's only one attractor, where the magnet and force of gravity are pulling towards the same direction when you look at their radial component, right? So in this case, you expect periodic behavior, and you expect it to be quite similar to a normal pendulum, except you'll get jerkier motion down the bottom. I'm just making a note that whilst we put drag in one direction, that's just an artistic choice. It could be the other depending on the direction of velocity. So when it's in a different direction, then we get those different directions, which is the cause of the unpredictable behavior. Alongside with this over here, there is a really high force dependence, position dependency for the force. So what we expect is, so that's the chaos. And when we expect near the magnet, we expect it can be either at a high velocity, it will be like slingshotted off, like in that, that diagram there, or it can be get caught in an orbit where it will tremble around that point. So onto our quantitative model, right? We need to model the magnetic field and forces, then we need to include other forces and move on to our key predictions. So our magnetic field and force calculations. What you end up getting is this formula where the magnetic permeability of the vacuum we know as a constant, 4 pi, also a constant. And if we're looking at the field at the point, we get to choose the vector for to the point in the field, and that also chooses the unit vector there. And from this, we can get via regression the magnetic dipole moment. This predicts a field like that, and that is the field strength for all the points on the magnet, which shows how position dependent it is. Because between, like here I've put the maximum the pendulum can go without flipping upside down. So between that maximum and about 0.5 is less of a change than between 0.5 and 0.4 in the field strength, which means a very significant difference in force. I have done regressions for the magnets that we use later in experiments in the appendix. I can show them if you want. So the force of the magnetic is just the gradient of the magnetic dipole dot the B field, which is because of that 1 over r squared, like the distance proportional between the dipoles getting smaller. So the ends of the dipoles getting smaller. So there's going to be a torque to align the magnet with the field. This is really large compared to the moment of inertia. So we are going to assume that it instantly aligns. All right, gravity dissipative forces and tension. Force of gravitational is just mg down. I think that's pretty simple. Based off observations, we're going to use linear drag. Here we've done a regression on the pendulum without base magnets because we don't think eddy currents are significant, and that allows us to test that assumption. Here we have the force of tension. That's just so that it's not moving up and down. And then we can just add these together, get the acceleration, and now for a given position and velocity, we can know the acceleration. So what we've done is we've simulated this with RK5 in Python, and we get that divergence of paths that we see initially. And we can see that even from really, really close starting positions, there can be different final endpoints. Those were released less than a millimeter apart. That is chaos in a one-magnet system. So onto our experiments. I have also proved it's chaotic in the appendix. So this is our setup, and that is us showing it tracking just in terms of how accurate it is. For this, just in that setup earlier, if we did it as is, we would get parallax. So we've accounted for it using these formulas. Happy to go into more detail later, but that's so we're going to look at the distance the magnet is offset from the center to see about the attractor interactions, and we're going to change that attractor strength with the distance from base to pendulum attachment. So underneath there, see those dotted lines? That is the that's the simulated value where I have put the uncertainty in position, because that gives us information about how position sensitive it is. I haven't included the other uncertainties, which is why the experimental is outside the theoretical's prediction. I'm happy to go over that more in the discussion. But we see, when it's right over, we see that normal pendulum behavior. It's basically moving in a straight line. And as it goes, it starts to get slingshot around. This changes into sort of orbits around, like it's changing it into an orbit around the gravitational attractor, and then we get to that. We see between them decent agreement, and we see very large variation between trials, which is because the system is chaotic. And in our theoretical predictions, we haven't accounted for uncertainties with velocities. And what we get is, when we offset it 9.5 centimeters from the center, we got multiple different initial, like from the same, basically the same release conditions. We ended up with magnets over different attractors. You can see how close they are up there, and then they diverge, and we get that same result theoretically. Most of them end up there, which matches the fact that we got 2 ending up on this one versus 1. And even before then, we can start to see orbits around the gravitational center, even if it ends up there when the magnets are sort of far apart, but not as far apart. So then we've varied the height, which means it changes how strong the magnetic attractor is in the manner that we thought was had the least flow-on effects. And we see decent agreement, but we see some disagreement that I would like to talk about in the discussion. And then now we move on to the 2-magnet case. We're going to call one of the magnets base 1, and then second base 2, just throughout so there's no confusion. And when we release it, I've put crosses where the magnets are on the bottom. We see that it tends to be, ends up being only around the 2. Getting the 3 magnets movement is extremely difficult because it ends up tending to just move back and forth between two attractors. So we start with the force, to model this, we start with the forces in the one magnet case, and we add in the force from the second magnet. So the force from the magnets are independent. You can figure out the B field due to one magnet, and then it's just m dot, the gradient of m dot the B field due to that magnet, and then we just add them together. We get back to our same equation, and we can simulate it again. And here I have shown the three magnet case, but it is reliant on symmetry. And it's very similar to the one magnet case, just I will explain that later. So now on to the two magnets. What we see is, I would like to discuss some of this later as well, but we see the divergence of paths is larger with the two magnets, and we also see that there are similar things because of that. The two attractors don't interact that much, and there's okay. Now on to our conclusion. We consider the forces involved to come to a quantitative model. Based off that, we simulated it, and we found that it was chaotic theoretically, and then we went on to the two magnet case. We used a modified version of our earlier formulas, and we got that it was also chaotic. We then experimentally verified the the offset, the height to magnet, and the one magnet versus two magnets. That's our references, and thank you.
Mentioned. Have you calculated Ljupunov exponent
Yes.
in order to determine?
Do you want me to show you it?
Just a quick showing.
There, that's for the one magnet, and that's for the
Okay.
two magnet case.
Thank you very much.
just shown-
Can you give me in
Or,
brief?
like,
no,
the
it's fine.
gradient
Can
of
you
that.
give me a brief definition of what chaos is?
Chaos is that the differences in initial conditions grow exponentially with time, whereas if it was stable, they would decay.
Okay. Thank you very much. How large are your magnets in size-wise?
I will show you, the magnets were about 2 mils thick and had a radius of about 8 mils, but I can also show you the...
Okay, no, that's fine. How strong are your magnets?
I'll show you the regression that we did. It was about, we had a magnetic dipole moment of about 0.5 and 6 for most of them, although it varied slightly. We did account for this in our simulation.
So essentially, it was a bit unclear. Can you just clarify what parameters you additionally independently varied?
Oh, okay. We changed the height from the base to the
So the
pendulum
releasing-
attachment.
Okay, so the height, yes.
And then we changed the position of the magnets on the base, and we
Yes.
introduced a second magnet.
Okay, thank you very much. Is in the video you shown us, is this in string you used, or because
Yes,
it
we
looks
use
very
string.
taut on when oscillation?
We use string. It is a sort of plastic string.
It looks very large in the video.
Yeah, that's because
So-
I've zoomed in.
Okay.
I've only looked at the bottom,
and
not the
then
entire
for data
thing.
evaluation, did you do tracking, or how did you evaluate the
I use
experimental
tracker.
data?
Do you want me to go?
No, it's fine. Am I clear? You already have accounted for parallax error, right?
Yes.
Okay, then thank you very much, and we will talk.
I didn't check it. Okay.
So hello everyone, I'm Baum and I will be doing the opposition on this year's task problem number 9, the magnetic assist. We already know the task from the reporter, so we'll further move on what we would have liked to see in this report. We would like to see a basic principle described with the interacting magnetic fields and the potentials then causing actually different phases in this phenomenon. Also, which is essentially a bit harder, we would like to have seen a reproducible motion measurements for different parts on the motion, such as frequencies, resting positions, and also the patterns. For the parameter variation, what we'd like to see are different initial conditions, vary the magnet size and strength and positions, the string length, and for the theoretical modeling, we would like to see theoretical modeling of the magnet and also covering spatial and tilting motion. Now, for the experiments, what we really liked is that you show the video of the phenomenon and you also independently measure the dissipation and you perform video tracking. However, we were unsure if the string you used was actually appropriate since it looked in the video very huge and always thought, and therefore we were not sure about this, but we can discuss this later. Also, there were claims in different trials that is due to chaos. We think that this is here a bit misunderstanding of what type chaos actually is in the system, and it's essentially then also a bit unclear for also the one or either two magnet case, and we were also missing some very important parameters such as the initial release conditions, the string length, but now further moving on to the theory part, we really like you to actually calculate the magnetic force using the dipole approximation, whether we are a bit unclear if this is on the size of your magnet actually applicable, and using RK 4.5 numerical integration method. Also, the basic explanation was, in our point of view, a bit lacking because you only explained the relationship between forces and distance, and therefore we would like to have seen more how the actual forces then actually change the motion, and also how they affect the different parts on the motion, such as the resting position, the frequencies, and then also the patterns. Also, the limits were not really discussed, as I mentioned earlier. The dipole approximation assumes 1 point, and we are not clearly sure if this is actually applicable in this case. We can discuss then this later on in the discussion. Also, we think that there's no sufficient theory experimentation comparison for both 1 and 2 magnet case, since it was a bit unclear and the plots weren't really understandable. Also, the different parts on this motion, such as when the gravitational force or the magnetic force overtakes one another, wasn't investigated, and also the missing account for the tilting orientation, which was actually drawn in your basic explanation. So therefore, we missed a bit on that part. For overall impression, continuing again on the fulfillment criteria, we think that the basic principle of the interacting magnetic fields was okay, but we think there's still a bit improvement. For the motion measurements, we missed the frequencies. However, on the parameter variation, there were some parameters variated, and we can conclude to say that the task was partially fulfilled. And now I invite you to the stage. Okay, so sorry. First of all, I'd like to start with your Lyapunov exponent, which you already shown in your appendix. My question here is, from which point was this divergence then actually measured?
Sorry, so you're asking from what point was that?
Yeah, you can just go to the slide and you show again your Lyapunov exponent. Yes, but okay. Yeah, no, my question is more based on where did you calculate this Lyapunov exponent in your configuration of parameters. So in order to clarify this a bit up, so when you have your magnets like here and there, where exactly did you then calculate the Lyapunov exponent? Because I think this is really crucial
It was
for...
out. So calculated the Lopinov exponent when it was released from out here.
Okay, so from out here. Would you think that you have a different Lopinov exponent when
Yes.
calculating it from here?
Yes.
Okay,
because-
so then I must say I would disagree on with you to the point that this whole phenomenon is chaotic. I rather would say that it can be chaotic in some cases depending on the resting position. Would you agree with me?
Yes,
here?
I would agree with you. What I'm trying to say is this is a system that demonstrates chaos,
Okay.
depending on how you set it up. Obviously, like I have, when the magnet is directly underneath, I don't think there's chaos there.
Okay.
That's in one
Okay,
example.
so I think this was a bit to clarify on this. But furthermore, what I was missing a bit also when talking about chaos, you said that you can't predict actually the motion in
Can predict it initially. That's why
Initially. So
that's why I
only
showed the
in-
graphs,
so-
and you can predict it probabilistically long term.
Okay, so only in the you always in the graphs you showed only the first few
Yes,
seconds.
because after that,
Okay.
the divergence
Okay.
is so large that it doesn't make sense to compare them.
Okay, then further going on this point, in this first few seconds you are showing to us in the graphs, which force is here actually the most important force?
It depends on what setup you have. Because if, so let's go here. Let's go
Yes,
back
you
to
can.
these slides. Because you get at long distances.
You can maybe show just some measurements. Yeah, okay.
At long
Sure.
distances, you get the normal behavior like a pendulum, so there gravity dominates.
Yes.
But you see that slingshotting motion, like here, you wouldn't observe that with a normal pendulum, would you?
Okay, so you mean here this is the slingshotting motion you're talking about?
I'm talking about how, see, over there, that's the 9.5 centimeter offset.
Yes.
When you're around there, what happens
Okay.
is it gets turned
Yes.
around, basically.
Yes, I fully agree with you, but you agree with me here that the gravitational motion is is the most important force in this part. So in the first few seconds you're showing, right?
No, I disagree, because it does still go near the magnet. The gravitational force dominates for the large majority of the time.
Okay, so
but
then
when
we
the
can agree
magnetic
on the
force
magnet-
does dominate, it changes the motion significantly.
Okay, so with smaller, then I can see that we can agree that with smaller distances, so like when the pendulum is directly here, what you're essentially then calling the slingshot motion, then the magnetic force is overtaking. So it's
The magnetic
the most
force
dominant.
is dominating there.
Okay, so then therefore, when looking at the full motion, sometimes after a certain time, your pendulum, as you also shown in the video, only oscillates like above one attractor, right?
Yeah, that's because drag, you get dissipative forces, the energy is decreased, and it has to be in one of the
Okay,
attractors.
so then therefore I wouldn't state that it is chaotic throughout your whole system, even if you start like right behind
It
here.
is not chaotic for the entire time because drag exists,
Okay.
but there is initial chaotic motion, and drag is quite small because you have that non-magnetic and non-conductive base.
So
the
we
eddy
can
currents
agree
aren't
that in
significant.
the first part of the movement, there is that is mainly for the most time gravitationally dominated, and for the last part where it's only hovering when it loses its energy due to drag, only mainly hovering above above one magnet, and then there is this mainly magnetic dominated, right?
Yes, but if it's really close to the magnet,
Then there is
You're gonna get the trembling motion.
magnetic dominated,
Yeah.
right? So to sum this point up, I would state that we have actually transient chaos in this case here, because in the first phase you can see that one can predict it with a simple model, and in the last phase is mainly hovering above one attractor. So therefore, I wouldn't state that it is an whole chaotic system, but mainly reduce this down in order to clarify this up to a transient chaotic system, since this was a main part of your
It is
report.
transient chaotic, but the thing is, even with that, I've released it from quite far away, but you still do get
Okay.
chaos
So we
in
can
the
agree
motion.
that this is a transient chaos phenomenon.
Yes.
Okay, very good. Then we move on to another point, being your experimental setup. Can you go to the slide
Yes.
where you showed this video?
The video or
With two
the...
magnets. With two magnets. where you show the
Here?
video of the motion. Yeah,
What one?
exactly this one. And maybe you can show it shortly.
What one? The first one or the second one?
The second one is perfectly fine. So when looking at this, how large is this distance from above? Because the string looks actually really large
It's.
from his width.
Are you
The string looks actually really width.
Okay, the easier way to see it is compare it to my fingers. You can see how wide my fingers are.
So I think this is a pretty significant. Width in order to also account for air drag. But
It is a significant width, but we did calculate
so
air
you
drag.
so you counted the air drag for this string.
We did a regression to get the
Okay.
drag, which would have included drag
this
from the
is-
string.
This is perfectly fine. But then furthermore, how is this magnet fixed? Is it like fixed that it's always normal to the magnetic plane, or can the magnet tilt?
Are you talking about the suspended magnet or the base
Yes,
magnet?
the suspended magnet.
It's string. It's attached. I've
so
got
it's so it's
string
so
tied
it's
around.
always like normal
It
to the
can
plane.
tilt.
It can tilt.
And do you want me to go to the explanation? I've got in
So,
the appendix
I think-
justification
yeah,
why.
I think that
assuming
the
it's
tilt
aligned.
is actually a crucial part because when you think about the magnetic torque, then the magnet, which we can also see in your
Here, I've evaluated why I think assuming it's always instantly aligned is reasonable. We only see small angles in the change. I'm sorry that it's
So the change
kind
of-
of blurry, but
Okay.
the angle doesn't change that much, and the moment of inertia is quite small, and that change of angle is what we would predict based off its position.
So for the assumption that it always aligns in the B field, the assumption is that the change of your angle is way greater than the change of your tilting is way greater than the change of your motion.
No,
right?
the assumption is that it will align quite quickly because we have quite a high force. Look, I've done.
Yes, I see that quite high force, but how is
Compared
this
to that.
justifying this alliance in every time step?
Oh, what I'm saying is if there's a really high torque, right, it's going to accelerate
Yes.
quite fast.
So the torque is larger than the force.
I'm sorry, can you explain to me what you're trying to say?
Okay, what I was trying to see if it's actually justified to say that the magnet always aligns within the B field, and therefore we would like to have seen that you present to us that the change of this tilting angle would be then also greater than the change of the spatial angle, because this would be the assumption behind this.
Sorry, why are you trying to say it's greater than? I'm just trying to come. Why do you think the tilting is greater than
Okay,
the
so
change of that?
so I think we are
Okay.
misunderstanding on this point. So there's
The
another
reason
point.
I'm just saying is the torque is higher than
No,
the moment of
I want to
inertia.
talk about more a bit about your setup and want to stay on this point. How did you ensure your initial conditions?
You will see. Let's.
Did
go back.
did you release the magnet by hand? Is the main question.
Yes, I did release it by
And-
hand.
okay.
But I checked that my hand didn't
Okay.
interact when I looked at the video, and also you can see that I've released it from in there, so that means the position.
Okay,
was
so you
constant.
could in some part ensure the starting conditions are for different trials always the same.
I could ensure that the starting positions for different trials were incredibly similar.
Okay.
However, they would not be exactly the same.
Okay, so summing up this report, we discussed about Lyapunov exponent and chaos in the system, because it was actually very unclear what chaotic system she was talking about in the report, and we cleared this up in order to look at and what phases different forces are the dominant ones, and we could come to the same agreement that we have actually transient chaos in this phenomenon. Also, we agreed on this. There are several phases, one where the gravitational force is the most dominant, and one where the magnet force is the most dominant, which is really a crucial part on this motion. Furthermore, then we explored her experimental setup and we looked at whether the string was actually justified, and was the neglecting of the tilting motion, so just to be it always aligned in the magnetic B field, also justified. And with that, thank you very much for this nice discussion.
Okay, so to start with, I would like to ask some more questions to the reporter. So, did you change the initial conditions in any time to see how the system and the whole system would react? Yes or no?
I did, but not. I haven't got graphs of that.
Okay, so you did it, but you didn't show it.
Yeah.
Did you see significant difference?
Yes, you do have the sensitivity to initial conditions, which we see through the trials.
Okay, thank you. You said in the also question to the reporter, you said that there is chaos in the case where only one magnet is present. Is that correct?
Yes.
Okay. Does the opponent agree with that? That there is chaos only with one magnet present?
Or transient chaos.
Yeah, I would agree to the statement of transient chaos.
Okay. Moreover, I would like to ask the reporter, how did you experimentally measure the Lyapunov exponent?
I have not experimentally determined it, but we see that the divergence is.
Okay, so you haven't experimentally measured it.
I used the theoretical thing, and we see the divergence.
Do you think that, to the opponent, do you think that this would be important to be measured experimentally, or is it fine?
I don't think that calculating Lyapunov exponent with this insurities of the setup is even possible, so I think this is perfectly fine. Okay,
thank you. Also, question to the opponent. How you talked about the tilting of the magnet, and the reporter said that the tilting was relatively small in this case. Do you still think that it's crucial to the problem?
Yes, I do think that also the direction of the magnet with the alliance in the B field also increases the magnetic force, and therefore it's very crucial to the problem.
And again, a follow-up question. How would you account for this tilting? What was your suggestion to account for this tilting?
So my suggestion would be modeling both the gravitational, centrifugal, and magnetic torque acting on this tilting motion, and therefore solving for a different differential equation too, which would be possible with ERCA 4.5.
Another question. Do you have to?
Can I add on that?
Sorry. Okay. I want to ask you another question on that. On a different part, you showed all these graphs, and because they were kind of complicated, did you use any theoretical equation to calculate the theoretical the trajectory, the theoretical trajectory, the theoretical line?
Yeah, I've got the dotted line underneath. Do you want me to go
did
back
you,
and show
Did you use an equation presented here, or was it
yes,
only from simulation?
I used the equation to get a simulation.
Okay, thank you. And one last question to both of you. You used an equation to calculate the magnetic force, but do you think, did you account for the magnetization effect that may occur because the magnets were relatively small?
Wait, sorry, can you repeat again?
Did you account for magnetization anywhere because the magnets were small, were close together?
We do not think that would be
do you think that this was crucial to account for, yes or no?
So magnetization and dipole moment are essentially the same in the relation to volume.
Thank you. Hello, my name is Bakos, and today I'm doing the review for Team Greece. Okay. Okay, as I said, I'm Bakos, and I'm going to do the review for problem number 9, magnetic assist. We are all familiar with the problem statement, so I can continue. So about the evaluation of the report, the positive aspects is that the reporter analyzed the aspects of the report, analyzed the aspects of the problem, and performed a basic force analysis, gave a clear depiction of the magnetic field, and also cite some sources on its slide. Moreover, he used a complex theoretical model and addresses his assumptions, which was important, and he tried to address the chaos. Moreover, there was a clear breakdown of the phenomenon and labeled graphs, conducted multiple trials, and lastly, as it was proven, he took parallax into account. About some negative aspects, there was unclear demonstration about the phenomenon, so only a few videos were present. The initial conditions were not that explored. They tried to have them studied, but it wasn't sure. There was also an unclear and confusing depiction of chaos especially before the discussion, and did not consider magnetization. Moreover, he uses a matrix for a gravitational force, which was not explained, and we think that he should explain that, and there was no error bars in the graphs. Moreover, most of the graphs, in our opinion, were kind of unclear, and there wasn't he didn't investigate the actual motion of the magnet. About the opposition, we have the positive aspects, so he questioned the magnetic moment and the strength of the magnet. Moreover, there were mentions of the lack of error analysis, and he asked about parallax, which was an important error. Moreover, he offered his own opinion on most of the points raised and his expectations in the presentation. He referred to the producibility of the experiment. He mentioned the tilting motion, and also mentioned the missing and the lack of variation of parameters. Lastly, he questioned the initial conditions and the conductivity of the base, which is important in the problem statement. Also, he mentioned the lack of the theory and the experiment comparison. About the negative aspects, he mentioned the magnetic strength as a parameter, although it was not quantified through magnetic moments. And lastly, he did not account for the magnet rotation, which could have caused a small error. About the discussion analysis, the reporter said that chaotic motion could be predicted initially, while the opponent disagreed. And in our opinion, opponent was correct, because with this experimental setup, chaotic motion could not be accurately predicted. About the forces, the reporter said that the normal pendulum, the opponent said which force was the most important, and the reporter answered the normal, the pendulum-like behavior, gravity, so the gravity is more dominant, but only for the majority of time. And in this one, we also agree with the reporter. Okay, so about the third point, about the experimental setup, the opponent asked about how large is the distance from above, because the string looked abnormally large, and it could cause additional air drag. And the reporter said about a regression to find the air drag. In our case, we agree with the opponent, because the width of the string could play a role and have an error. Okay. The last one was about the string attachment, and the opponent said how was the string attached to the magnets, and does it allow for tilting motion. In our opinion, although the reporter said that the angle doesn't change much, the moment of and the moment of inertia is small, we agree with the opponent, and we say that the tilting can cause an error. About our missed points, we think that both the reporter and the opponent missed the slight rotation of the magnets, which may be difficult to actually calculate experimentally and to quantify too, but it should be at least mentioned as a possible error that could cause an additional deviation to the experiment. Thank you for your attention.
If you want, you can also talk in this mic.
Always aligned with the B field, which is due to the fact that we get the torque is 100 times larger than the moment of inertia in the direction that we observe the most motion. which means in the parts of where this is relevant, we do not think this would have a significant impact on the motion, and we also had an alternate model earlier, which we found that this did not have a significant impact on the motion. F equals mg down, the matrix is just a vector. The system is definitely transiently chaotic, and chaotic motion can be predicted initially, because if the error grows exponentially with time, right, then at small time values, whilst it grows exponentially, you are still going to have a small growth in uncertainties, which we saw by the fact that our trials were initially very, very similar, but towards the end they did diverge. So, based off this, we think that we successfully showed chaos in the one magnet system. We extended this to the two magnet system, and we modeled this in a way that we thought was appropriate, and we experimentally verified it. Oh, okay. We don't think the tilt is a critical part of the motion, as the tilt was small and the assumption we found to be reasonable. The magnetic dipole approximation was reasonable, we found, and
Time is over. Now, your questions.
So first of all, I have a question for the opponent. What is the difference between a chaotic system and a, what was the word you used, transiently chaotic system?
Transient chaos. So it's this is not a clear difference. There's just different types of chaotic system, and just stating that there is chaos in every case, which is in this phenomenon just wrong, because we only could observe chaos in the second phase, which we are currently talked about, and this is therefore why I wanted to clarify this.
Okay. For the reporter, unless somebody else wants to, okay, but for the reporter, I want to ask, do you think, or was there any check done to make sure that the numerical instability during the numerical...
yes, I've used
and what was it?
It was numerically stable.
How
I've
do you
used
know?
an inbuilt function, and I have changed, I changed the acceptable error range, and I have also used an alternate model, which unfortunately is outside the 12 minutes of the report, and I found similar results. Do you want anything else?
So you use different step sizes?
Yes, I changed the, what I've done is I've used the SciPy inbuilt thing, which has an error bound on
you used
the...
4.5, correct?
Sorry.
RK 4.5.
Yeah.
Yes?
Which has, so that auto adjusts the step size to keep it bounded in the error, and if it's not, SciPy will raise an error.
Okay. And yeah, somebody else?
Yes, also on the Lyapunov exponent. Can you clarify what was the perturbation of which order was the perturbation during the simulation?
For the simulation, what I did was 10 to the power of -8.
And it was for coordinate or velocity?
For coordinate.
Okay. And can you open this slide, actually? Yes. Also, does this simulation take into account the friction?
Yes, it takes into account the effect of drag, which is why you see that stabilization up there, which is where friction has, that's where it's going into trembling. You know how we were talking about transient chaos? It's chaotic, it's not chaotic after it has a very low velocity in terms of the fact that it's trembling. You start to know more about the motion.
I mean, here it is everywhere chaotic. The exponent is higher than 0 everywhere. Almost, okay, except of first 1 second. But by the way, do you consider both scenarios like chaotic in the same way? I mean, the value of the exponent is the same, 25, which is enormous value actually, and it is strange for me.
I simulated them in the same way. Do you want me to? I've got my code. I can show you my code.
Like, not really. Okay, I will not spend much time.
for the reviewer, I wanted to ask, what do you think the magnetization effect might be relevant, and how would it occur?
Because the magnets are placed too small with one another. I think that the actual magnetization could occur between the magnets at the base and the magnet that is oscillating at the top. And although it may not change the problem significantly, it should be, I think the reporter could mention it as a possible error in his calculations.
Thank you.
So I've got a question to the reporter. Did you perform this experiment with a number of magnets, different magnets hanging from the string and a different length of that string?
I did perform them, but I've only got qualitative videos. I don't have quantitative stuff on them. Do you want to see the qualitative videos?
Maybe you could show one video.
Okay, can you go on to another question while I get the videos up? That way. Oh, okay, yeah, go on. I'm sorry, my laptop powered off unexpectedly. I tried to turn it back on. Can we extend the jury questions considering that? Oh, actually, I can show you it on my phone, but that's...
It's fine.
I might be able to get... do you want me to still try? I can...
Okay, I guess that the jury question is over, and we will sum up our scores. Okay, we are ready to show our scores. Scores for the reporter: 5, 5, 5, 5, and 5. Scores for the opponent: 7, 7, 6, 8, and 7. Scores for the review: 6, 6, 6, 5, and 6. For the report, we don't have any difference, so whoever want to explain.
So maybe I will start because I'm the first one over here, next to the chair. So I just have to admit that I'm impressed by the knowledge and the information about the phenomena that you have presented to us. So that was just amazed that you know what is going on, how the system is chaotic, why it depends, how it behave in a certain way, what are the important points. So everything is very, very high quality. But where did it go to show this in a more, let's say, organized, and we have this point here, science communication. That's the thing that has to be improved a bit. So that makes this great for you, and I own you the partial marks, so it's 3 for report and 125 for the discussion, so altogether sums to 5.
Okay, thank you. And for the opponent, we have 1, 6, and 1, 8. So for 8, please.
Yeah, so basically you asked almost everything I would ask if I were the opponent. I gave you 2 for the question asked, 2.25 for opposition speech, 2.75 for discussion with reporter. I wasn't really happy, to be honest, with the fact that you just asked this set of same questions by cycle during question, during opposition, and during discussion, but there is no such, how to say, I have no opportunity to take grades from you by score sheet. Yeah, so that's how the aid occurs. You just raised all important from physical point of view topics, as I think. You didn't spend much time just clarifying, how did you do something in experiment, how did you suspend this magnet, and so on. So that's it.
Okay, and I gave the low score of 6. So the partial grades are 1.5, 2, 2, and minus 0.5. So for the questions asked, I feel like they were relevant for the most part, right? I mean, everything, as you said here, everything that I probably would have asked, you asked as well. Maybe not everything, but relatively speaking. And then for the speech was comprehensive, it was efficient, everything that needed to be said, it was good. There were, at some points there were some small time inefficiencies perhaps with the reviewer later on, but in any case, that was pretty good. The discussion is where I didn't like it so much. I feel like a lot of time was spent on perhaps slightly irrelevant things, such as the transient versus non-chaotic, or the ordinary chaotic system. And yeah, that's basically it. But overall, it was pretty good. and the questions about the setup in particular were accurate. I would have perhaps asked more about the numerical thing myself. Okay. Well, good job.
Thank you. And for the reviewer, we have many 6s and 1 5. And for the higher side, maybe Diana?
I don't think I ended up that high. I ended up with 5.5, and I rounded up it to 6. I think like your quick questions were pretty good. You did a good job asking both reporter and opponent, and you raised the good points there. Review of the both report and opposition were pretty average. One thing that I subtracted points ended up, and that's why I ended up at 5.5, was that at the miss points you pointed out something that was really well discussed, in my opinion. So that part I didn't really like, but it was just 1 point. Other than that, you did an average review and you did a good job asking questions. So with the partial points, that ended up at 5.5, and I prefer to round up.
Yes, and I gave the lowest score 5. Partial scores are 1.5, 1, 0.5, minus 0.5. So you asked a lot of good clarification questions, I think, but your review itself, both of the report and the opposition, was rather superficial. I mean, a lot of physics, as I mentioned before, was discussed, and you didn't really cover it during your review. Also, as Diana said, you mentioned as a miss point that the opponent team didn't ask about the self-rotation of the magnet, which obviously was discussed. So I took a 0.5 for that. So that's it.
Thank you. And from student, do we need any more specific explanation for any marks? No? Okay, then let's end the stage